Okay, ideal gas, ideal gas. Okay, I get it, I get it. All right, wait a second. What? All right, so now I want to talk to you about real gases. All right, this is I feel. First of all, I think I warned you at the beginning of the chapter that in our last section we would say, all right, let's talk about real gases at some point. Now it turns out I've been saying all along PV is equal to nRT. But I've constantly said for an ideal gas. All right? So PV is equal to nRT, and this is an excellent approximation. But it turns out, in reality, there are two corrections that we've got to take into consideration. All right? Very small portion of your of what you've got to worry about in terms of being able to understand gases, but it matters. Okay? So let's talk now about real gases. It turns out that an ideal gas has a molar volume. Do you remember this from section, I don't know, 5.2, I don't know, 5.3? We had the molar volume of an ideal gas, and we found out that a molar volume of an ideal gas was 22.41 liters. Well, it turns out that chlorine at a particular temperature doesn't have exactly 22.41. Chlorine gas, right? It looks like this. CO2, carbon dioxide, is closer to an ideal gas, right? Ammonia is closer yet to an ideal gas. Nitrogen gas, which is what's in the air, is very close to an ideal gas, right? You see that, 22.4? Helium is even closer, right? Look at that, 22.41. Okay, all right. So you can see that to a pretty good degree of approximation, the molar volume of a gas is 22 liters per. I'm sorry, 22 moles per liter. I'm sorry, 22 liters per mole. Sorry. Okay. It says it right there, right? 22 liters per mole. Okay. That's the molar volume of a gas, of an ideal gas. Now, of a real gas, it turns out there's some slight variation. What does it depend on? Well, it depends on particle volume. Remember in the beginning I said that we are assuming the particle is negligibly sized, its volume is zero? Well, it's not actually zero, right? So let's take a relatively big atom. This is just an atom, argon. And let's say that the volume, it's not really that big actually, but it's big enough to discuss here, okay? So let's say that if we have, if we take a mole of it, that was the molar volume in STP, by the way, in the previous question, okay? Now here's, oops, crud. All right, so let's take here, not an STP. This is not STP, no. It's at 500 Kelvin and at increasing pressure, right? And this is an atmosphere, so 1 atmosphere is way down here, right? That's 1 atmosphere here, okay? So you can see at 1 atmosphere, argon gas, right, that's going to be here. Can you see how that's just joining with that curve? Okay. So 1 atmosphere at STP, you can imagine argon's going to be pretty close. All right, so, but it deviates. Well, how much? Well, when the pressure gets extremely high, it turns out that argon and an ideal gas become different, right? What's an ideal gas? I mean, this is what we would calculate if we were assuming argon was ideal. This is where argon really is, and you can see that it deviates as pressure goes up, okay? Right, so I think we're going to see the same thing as temperature goes down as this gets really cold. As this gets really cold, as temperature goes down, cold, brr, right? Look at that. This is, where do we live? If this is in kelvins, this is about where we are, right? 300 about, I don't know. That would be more here, I guess, okay? This is about where we live. This is about room temperature, okay? So xenon gas is pretty close to the pressure, okay? But we find that due to the effect of intermolecular forces, as things get really cold, they get further and further away, okay? This is where N is equal to 1 mole and the volume is 1 liter. If we decrease the temperature and get down really cold, it turns out that the intermolecular forces, that is these two xenon particles, become a little more sticky. That's what intermolecular forces is, okay? We'll get into that in chapters 8, 9, and 10. No, 9 and 10. But these become very sticky as the intermolecular forces get bigger, okay? I said 8, 9, and 10. I really think it's chapter 11, but I'm done there, okay? It's chapter 11. We're talking about intermolecular forces. But it turns out that as the temperature gets cold, these guys become sticky. Okay, so these last two slides have just shown you some deviations from ideality, right? Where the red and the green curves separate. Okay, now let's look at this. Tell me which of these boxes would best represent a gas that was ideal. Which of these would be most ideal, right? And remember, for an ideal gas, we have these two postulates. One of them is size is negligible. Negligible. And the second postulate is that do not interact. They do not interact. Okay, those were the two things for an ideal gas. This was ideal. Okay? So can you see that these are not small? So it's not this one, because they're not small. And can you see that there's more over here? So these are more likely to interact. More likely to interact because they're closer. Man, where's my handwriting? Because they're closer. Okay? So it's not this one. It is this one. This is the closest to an ideal gas. All right, I think then all we're going to do now is we're going to, just one second here, let me look at my notes, make sure I'm not getting too far ahead of myself. Okay, now we're going to look at this and say, all right, well, we've got these two constants. I probably should have put this, you know what, let me go to the next slide. These are out of order. So this is the equation for a real gas, okay? Can you see how this looks like P, V, and RT, right? So it's not that different from an ideal gas. There's an ideal gas is up here in red, but here's a correction for pressure. And it's some term, which we look up in a book, table, and we look up that in a table, right? And moles, this is the same moles, these are all three the same, okay? And these are the same volume, right? So no big deal. The rest of these terms all look very familiar, but A and B don't, right? So don't worry about that. Suppose you had a table that looked like that, right? Can you see A and B? Here's my A term, and here's my B term. So what I have to know is I've got to know this equation. P, and I think I'm going to give the equation to you on the exam. Because I really don't, frankly, I know this sounds lame, but I just don't think it's that important for you to remember the form of this equation, okay? There's an additive correction factor for pressure and an additive or subtractive correction factor for volume. Can you see if B was 0, this term would be 0, and that V would simply be V? And can you see if A was 0, this term would be 0, and this would be P, right? So if A and B are small, then you can expect the gas to act like an ideal gas. If A and B are small, you can expect it to behave like an ideal gas. Let me look back one more time, and then I think we'll be done here. So you see these are pretty small. For helium, they're pretty small. For carbon tetrachloride, wow, look at that A factor. Bam, that is huge. All right, so which of these is going to be least likely to act like an ideal gas? Well, that one, right? Look at that A factor. So going back over here, all of a sudden for carbon tetrachloride, that was like 20.4 something, okay? So, and that's not, that's not nothing. So it turns out that's going to matter. All right, I don't think I have a sample problem to do with you here, so I think that's it for this section.